Hi, I'm Herb Gross, and welcome to Lecture 10 of Gateways to Algebra, where we will conclude our initial discussion of the game of mathematics. Recall that last time we emphasized that a game was any system consisting of definitions, rules, and an objective, where the objective was carried out as an inescapable consequence of the definitions and the rules by means of strategy. And we were showing that in the game of mathematics, that the rules of the game were called axioms. And in fact, if we leave out that fancy word, the only difference between applied mathematics and what we call pure mathematics is nothing more than whether the rules of the game are based on some practical thing that we can visualize, or whether they're simply an abstract system of rules that makes sense, but for which there's no known physical model. But let's go on with it. Last time we'd shown how we were going to talk about equality without mentioning what equality really was. See, for example, you have to be careful with equality. Let's go back to fractions, for example. Look at 1/2 and look at 3/6. Do they really look alike? If you didn't know what fractions meant, if you looked at 1/2 and 3/6, don't they look different? See, so we're not going to get into what it really means. All we're saying is what? That if 1/2 equals 3/6, then 3/6 equals 4/8, then 1/2 equals 4/8, et cetera, et cetera, et cetera. In other words, we're not talking about a whole bunch of other things that might be controversial. We're just getting to the things that we really need. And with that in mind, I want to talk about addition and multiplication. You may notice I just left out the words subtraction and division. And the reason for that is that with the advent of signed numbers, we never again ever have to subtract. We can always subtract by adding the opposite. And with the advent of fractions, we never again have to divide. We can always, in other words, we can always divide by doing what? Multiplying by the reciprocal. So the whole idea is going to be, we will give the rules for adding and multiplying, and then when people talk about subtracting and division, we'll say, no, we don't subtract, we're going to add the opposite, and we don't divide, we multiply by the inverse, by the reciprocal. So let me just come over here, pick up a card, and we're going to talk now about the axioms for addition. And for the rest of this lecture, A, B, and C will denote numbers. Now, the first axiom for addition is one we talked about last time. It's called the commutative property of addition. The commutative property says if you change the order in which you're adding the two numbers, the answer is the same. In other words, A plus B is the same as B plus A. And by the way, let me just comment for a moment on that that's a very, very important property. In most real-life situations, when you change the order, you've changed the meaning. For example, does it make a difference whether first you shower and then you undress, or whether first you undress and then you shower? And by the way, I'm not passing judgment. It's not that kind of a course. All I'm saying is, whichever way you do it, do you recognize that the other way is different? You see, it's a luxury in math to be able to change the order when you're adding without having to worry about changing the meaning of the problem. Those are the things that we want. We want to know what things can we change without changing the meaning of the problem. Because if the change changes the problem, then we'll wind up solving a different problem than the one we're trying to solve. At any rate, let's continue then. The second one says when you're adding 3 or more numbers, it doesn't matter on how you group them. See, in other words, if you first add A and B, then you add C, it's the same thing as if you added A to B and C. In other words, A plus B, listen to the voice inflection here, A plus B plus C is the same as A plus B plus C. And that's called the associative property because it says what? Since these things mean the same thing no matter how you group them, I might just as well leave the parentheses off. By the way, I didn't have time to write this. Let me give you an example of voice inflection that you might find interesting. In fact, maybe I do have time to write something over here. Let's just do something over here. Let me just write a simple sentence over here. I don't know how simple it is. They don't know how good meat tastes. Simple enough sentence. Can you see two completely different meanings for this sentence? See, is good an adjective modifying meat, or is it an adverb modifying taste? For example, are these people who have only eaten bad meat, so they don't know how good meat tastes? Or are they people who have never eaten meat at all, and they don't know how good meat tastes? Do you see how voice inflection makes a difference? It's like that little question in the Weekly Reader. One kid says to the other kid, hey, did you ever see a man-eating shark? And the other one says, no, but once in the restaurant, I saw a man eating tuna. Okay? It makes a difference how you inflect the words there. All we're saying is, in an addition problem, the answer does not depend on how you inflect. Let me just see what that means. So in other words, if I write down 3 plus 4 plus 5, the answer is going to be the same, whether first I add the 3 and the 4 to get 7, then the 7 and the 5 to get 12, or whether I first add the 4 and the 5 to get 9, then add the 3 and the 9 to get 12. It looks different as I get there, but the end result is the same. And again, for the person who says, let me see why that's true, I want to have a mental picture as to why that's true. Can you visualize his 3 tally marks, his 4, his 5 more, and the total number of tally marks doesn't change whether I shift these 4 closer to the 3 or whether I shift it closer to the 5. The important thing is, it doesn't matter whether I have this model or not. The important thing is, all I'm saying to a person is, will you accept this property? And by the way, it's not that self-evident that it works for other things. Look what happens with subtraction. Look at 9 minus 3 minus 1. One voice inflection says what? I'm going to read it from left to right. 9 minus 3, see, which is 6, minus 1, which is 5. See, 9 minus 3, that's one number, is 6. Minus 1 is 5. The other way would be 9 minus 3 minus 1, the same as if you were reading this from right to left. See, 1 from 3 is 2, 2 from 9 is 7. See, 3 minus 1 is 2, 9 minus 2 is 7. Which of these two is right? They're both right, but this is why you need the grouping symbols. See, for subtraction, you have to keep the grouping symbols. That's one reason why we like to add the opposite rule. See, suppose I say, hey, from now on, whenever I see subtraction, I'm going to use the add the opposite rule. What do I do instead of saying minus 3? I say plus negative 3. And instead of minus 1, I say plus negative 1. See, I add the opposite. Now this problem becomes what? 9 plus negative 3 plus negative 1. Once I have it in this form, notice that there are no more minus signs, just negative signs. This is now a pure addition problem, and now can I move these terms around any way I want? See, no matter how I add 9, negative 3, and negative 1, the answer is going to be 5. In other words, it will always come up to be this one over here. See, in other words, a $9 profit combined with a $3 loss and a $1 loss is always a $5 profit, no matter what order the transactions are in. But anyway, let me just go on with the next rules. And so far, what I'm hoping is that you agree wholeheartedly with every rule that I've written down here. In fact, I'm hoping you're saying these rules are too simple. When's he going to get to something hard? Because I don't intend to get to anything hard. I want these rules to say so simple that you will accept everything I tell you, and then we can really go to work on the mathematics. The third rule, the third axiom is for addition is there is a number denoted by 0. Notice I don't say it's nothing, I just say what? We denote it by 0 such that a plus 0 equals a for all numbers a. In other words, it's called the additive identity, meaning it's the identity because it doesn't change anything, and it's additive because it doesn't change it with respect to addition. In other words, you think of 0 any way you want. Is it true that for your definition of 0, if for example, I added 0 onto 3, would you agree the answer would still be 3? That's all I'm saying. You get the idea? You see what I'm saying? Just look at the rules as I write them and decide whether it agrees with your perception. Okay? Here's one that wouldn't make sense if we hadn't done signed numbers yet. This one says what? Given any number a, there exists a number b such that when you add a to b, you'll get 0, and b is usually denoted by the symbol negative a or the opposite of a. For example, what number, based on signed numbers, can you add to negative 3 to get 0? The answer is positive 3. So negative 3 and positive 3 are the additive inverses of one another, because when you add them, you'll get 0. And you see, this is the axiom that gives us the crossover to addition, because, to subtraction. Because now what we say is, let's just define the symbol a minus b to mean a plus the opposite of b. See, if I know what b is, this axiom tells me what the opposite is, and then I can just add that on to a. You see, in other words, this formally says what? From now on, subtraction is going to be add the opposite. Okay? Now, similarly, there are going to be rules for multiplication. The axioms for multiplication are pretty much the same as the axioms for addition, only with one or two minor changes. First of all, multiplication is also commutative. 3 times 4 equals 4 times 3. That's true all the time. In other words, the first number times the second number will always equal the second number times the first number. And if you want to visualize that, say like this, just think of what? Think of if you think of a rectangular array, 3 rows, each with 4 tally marks, is the same as having what? See, 3 rows of 4 is the same as having what? 4 columns of 3. We talked about that in the previous lecture. Okay, as far as multiplication is concerned, that's also associative. If you multiply 3 numbers, the answer does not depend on how you group them. And by the way, to again talk about what we're saying, notice that division doesn't have that property. Look, for example, at, I'll try to make something up here, 12 divided by 6 divided by 2. Let's just make up an example like that. Let's read it from left to right. 12 divided by 6 is 2. 2 divided by 2 is 1. If we read it from right to left, 2 goes into 6 3 times, 3 goes into 12 4 times. In other words, if I group it this way, the answer is 1. If I group it this way, the answer is 4. So does the grouping make a difference? Yes. Okay? Third rule says there exists a number which we denote by 1, such that for any number a times 1, which of course by m1 means 1 times a, is equal to a for all numbers a. That's called the multiplicative identity, and what it says is 1 does for multiplication what 0 does for addition. And then we have to have the inverse rule. In other words, is there a number you can multiply a given number by to get 1? And you all know from fractions that that's called the inverse or the reciprocal. So the rule simply goes like this. If a is not 0, for any number a, there exists a number b such that a times b will be 1, and we denote b by 1 over a, see? And b divided by a now means b times 1 over a. And just to make sure you understand this, what is the multiplicative inverse of 2/3? What can you multiply 2/3 by to get 1? And the answer, of course, is what? 3 over 2. See, if a is 2/3, 1 over a will be 3/2. And finally, one more rule, which is called the sign changer, and that says what? For any given number a, if you multiply it by -1, what you wind up getting is the opposite of a. See, -1 times a gives you that single number called the opposite of a. And all we need now to continue the game, you see, what's missing so far is this. We know we have axioms now for equality, we have axioms for addition, we have axioms for multiplication, but so far we don't have a rule that tells us how to do addition and multiplication in the same problem. And remember, how is this game played? I tell you what rules I want, and you're nice enough to agree to them. That's your end of the bargain. My end of the bargain is, once you agree to these rules, I can only use those rules to show what strategies we're going to have. See, I make up the rules subject to your approval. Once you've approved of them, I can only use those rules that you approved of. So no matter how self-evident something may be, if it's not one of the rules, I can't use it. So now I want one more rule. And that's the rule that's going to connect addition and multiplication. And that's called the distributive property. And what this says is, if a number multiplies the sum of two numbers, then the outside number does what? It multiplies each of the inside numbers. In other words, a times the quantity b plus c is you multiply a by b, a by c, and then add them. See? And by the way, you all already knew this. You know, basically, when you do a multiplication problem, did you notice what's happening over here? Every single digit in the bottom number multiplies every single digit in the top number. In other words, the 2 multiplies the 1, the 2 multiplies the 20, you add them up. This is a very common thing. And by the way, again, notice the use of the parentheses over here. You see, we have to have a rule because if I put multiplication and addition in the same problem and don't use grouping symbols, we have a problem here. Now, what's the problem? Look at this. If I read it from left to right, 3 times 4 is 12, plus 5 is 17. If I read it from right to left, 5 plus 4 is 9. 9 times 3 is 27. Remember the agreement that we made earlier in the course? Whenever multiplication and addition appear in the same problem and there are no grouping symbols, we always assume what? You do the multiplication first. Therefore, in order for you to know that I first want to add the 4 and the 5, I have to put that into parentheses. Now let's see what that says. 4 plus 5 is 9. 3 times 9 is 27. Okay? Now, I'm saying that's the same as if you said 3 times 4 is 12, 3 times 15 is 15, and 12 plus 15 is 27. I'm just saying accept that rule. You're saying to me, why should I accept it? Well, suppose you think of numbers in terms of being tally marks. Wouldn't 4 plus 5 be 4 and 5 more? And if I did that 3 times, wouldn't I just write this down 3 times? And if I write this down 3 times, don't I have 3 groups of 4 over here? And over here, don't I have 3 groups of 5? So in other words, all these tally marks, isn't it 3 times 4 plus 3 times 5? You say, yeah, that agrees with my definition. Somebody else may have a different picture in mind. The important thing is what? That this is how this rule works. Are you going to accept it or not? Has great application. Suppose I said to you, real fast, suppose you multiply 75 by 37 and then multiply 75 by 63 and add them up. What's the answer going to be? Don't use any paper, don't use any pencil, do it in your head right now. And the thing I want you to see is, think of this in terms of money. If you have 37 checks, each worth $75, and somebody gives you 63 more checks, each worth $75, altogether, don't you have 100 checks, each worth $75? In other words, notice the distributive property over here. The 75 multiplies the 37 to give you this. The 75 multiplies the 63 to give you this. By taking out the 75, do you see what's left in the parentheses? 37 plus 63, which is 100. 75 times 100 is 7,500. Look how fast you can do that problem. Look at the fast way you can estimate 279 times 99. See, again, think of what? If you have 100 checks, each for $279, okay, and you now lose one of those checks or cash them, how many do you have left? You have the 100, so you have 100 checks, you use one of them, you have 99 left. So 279 times 99 is 279 times 100 minus 1. 100 minus 1 is the same as 100 plus negative 1. Now by the distributive property, the 279 multiplies the 100 to give you 27,900. The 279 multiplies the negative 1 to give you negative 279. Adding negative 279 is the same as subtracting 279. So 279 times 99 is how much? It's 27,900 minus 279. And before you even do that subtraction, don't you have a pretty good estimate for the answer? Isn't it sort of faster than doing the regular multiplication? But I'm not worried about that. See, what I want you to see is how we use this. And by the way, that's just the tip of the iceberg. The way we really want to use this in algebra, see, what I'm showing you is some nice applications in arithmetic over here. But the way we want to use this in algebra is to simplify statements. Have you ever seen these kind of little riddles where it will say, changing one letter at a time, go from the word cost, say, to the word ears, and you might do something like this. You say, let's see, if I change the O to an A, this will become cast. That's still a word. If I change the C to an A, this will become east. These two letters line up. Now I want the S over here. How about change the T over here? You see what I'm saying? In other words, can I replace each word by another word? And even though all of these look alike, when you leave out the in-between ones, there almost seems to be nothing in common. See, that's the way we do algebra by proofs. Let me just see how much time we have for examples. Here's an application. Remember, we already have done things like this. We say, let's solve for x. X plus 3 equals 7. We say, well, that's easy. This is a seesaw. It balances. To get x by itself over here, we have to get rid of the 3. Since the 3 is being added, we're going to subtract it. If we subtract 3 from one side, we have to subtract 3 from the other side, so x must be 4. 4 plus 3 is 7. That's fine. But now we want to say, hey, that's one way to do it. I wonder if the rules of the game are enough to cover that. How can I show that this is true, not by waving my hands, but rather, waved my hands too hard that time, by one step at a time using the game of arithmetic? Well, I want to get rid of the 3, so the x will be by itself. How do you neutralize the 3? If I added negative 3, the opposite of 3, that would give me a 0. Adding 0 doesn't change anything, so watch how my strategy works. I say, okay, since these two things are supposed to be the same, okay, I can replace one by the other, so I'm going to do what? Add negative 3 to both sides. Now, by the associative property, I can switch the grouping over here. So I can now write this as x plus 3 plus negative 3. On the other hand, 7 plus negative 3 means 7 minus 3. By the rule for the additive inverse, 3 plus negative 3 is 0, so this can be replaced by x plus 0. This says x plus 0 equals 4, but the rule for 0 says what? X plus 0 is the same as x, therefore x is 4. Now this seems like a much harder way for getting the same answer. But the beauty of this method says what? I don't care now how you do this problem. My game says what? Everybody who's agreed to play the game now has to accept this fact, no matter how they explain this, because it follows what? From the rules of the game. See, let me show you another example. I was taught very mechanically, called the cancellation rule. If b plus x equals b plus a, I can cancel out the b's and say x equals a. I think we used that once in a different form in this class. If I know that 3 plus blank equals 3 plus 7, what can I be sure goes into the blank over here? Okay? It has to be the 7, doesn't it? Well, how can I show that? Remember what I just said. I can't use anything unless I can prove that it comes from my game. I've asked you to agree to certain rules, and now I have to live by those rules. So I say, okay, let's suppose I know that b plus x equals b plus a. Let me add the inverse of b to both sides. In other words, I'm saying negative b plus this expression must be negative b plus this expression, because we said what? When two expressions are equal, I can replace either one of them by the other. But now by the associative property, I can switch the parentheses over here. This gives me negative b plus b. See what's happening over here? But negative b plus b, technically I left out a step, because the way I worded things was I had it worded as b plus the opposite of b. This says what? The opposite of b plus b. But that's okay. The commutative property of addition says, so what? If you don't like this order, just switch them. It's perfectly okay. In any event, a number plus its opposite gives me 0. So this becomes 0 plus x, which to emphasize the point is the same as x plus 0. This becomes 0 plus a, which to emphasize the point is the same as a plus 0. What's the property of addition? The property of addition is that when you add 0 to a number, it doesn't change the number. So x plus 0 is x, a plus 0 is a, and therefore we have what? X equals a. And what do we now know? That that's compatible with the rules of our game. See, again, try to understand what I'm saying to you. If you can do this problem easier, that's fine. Nothing wrong with that. But what I'm saying is, suppose two people disagree. Suppose one person says, I don't think you can do that. The other one says, I think you can. What do you now do? You go back to the common rules that you've all accepted. And if the person can show that the result follows inescapably from the rules, then everybody has to accept it. Now, even if the thing is true, if it can't be demonstrated that it comes from the rules, it means it doesn't follow from that structure, so we don't accept it in the game. Like, for example, did you notice that the rule I gave for 0 was that any number plus 0 gave you that number back again? I never said that a times 0 is equal to 0. But watch how I can prove that, and we'll conclude our lecture with this. See, a times 0 has to be some number. How do I know it's some number? Because a is a number and 0 is a number, and when you multiply two numbers together, you get a number. Whoops, I better be careful. I don't remember a rule that said when you multiply two numbers, the answer is a number. I maybe better go back and say, hey, do you agree that when you multiply two numbers, you get a number? If you say yes, I say fine. Now we'll add that to our rules so this problem won't come up again. But now having this, we say now what? First of all, is it true that 0 plus 0 equals 0? Sure, when you add 0 onto anything, it doesn't change. Therefore, will A times this be the same as A times this? Yes. Can I still use the distributive property? Yes, A times 0 plus 0 is A times 0 plus A times 0. Now, what is A times 0? It's certainly some number which we'll call B. This says what? B plus B is equal to B. Well, isn't B the same as B plus 0? So I can now replace B by B plus 0. Now, can't I take, what did I just prove before? I said if the same number is added on both sides and the result is equal, I can cancel it. You see, I'm going to use a previous strategy to develop a new strategy. See, B plus B is equal to B. B is the same as B plus 0. So what can I do now? Cancel the B from both sides. You see, without the game, I could say, why can't we cancel? With the game, we've demonstrated that the cancellation property holds. And what are we left with? B equals 0. So any number times 0 is 0. Now, let me conclude with just a couple of remarks here. I certainly, at this level, am not demanding that you play the game of math as a chess expert. What I want you to see is what? We're going to have a handful of rules that we believe in, that you believe in, and the main purpose of this is to take it into the realm of algebra, go back to where we had an input, a program, and an output, and see if these rules will help us replace complicated programs by simpler ones. When we don't need to do that, we just won't invoke the rules of the game. When all of us are playing the game and we all agree to something, we won't stop to say, let's see if that follows from the rules of the game. But suppose 3 or 4 of you get really interested in this stuff, and you say, I wonder if we can prove this from the rules of the game. Is there anything wrong with becoming an expert in the game? No, but all we need for our purposes is some higher court to help us judge when we do something and how we do it when 2 or more people have a difference of opinion. At any rate, we'll see how that develops as the course goes on, but as usual, this will conclude our lesson by saying what? Study hard, have fun, stay young.